A lot of you got stuck on day 7, one letter actually T. So today, no Rhino, no Grasshopper, just an explanation. Welcome back to the series. Before we move on in the course, I want to stop and properly explain day 7 because a lot of you told me it moved too fast. This isn't a rebuild, we already built the pavilion. Today is just about understanding what actually happened and why. Here's the honest truth about day 7. It isn't a 10 separate tricks. It's really just one idea used again and again. Once you see that one idea, everything else falls into place. Imagine our spine curve is a piece of string laid out on the table. Now imagine describing any point on that string not with a ruler, just with a simple question. How far along the string am I? At the start, you are at 0%. At the very end, you are at 100%. Right in the middle, 50%. That percentage written as a number between 0 and 1 instead of 0 and 100 is exactly what a lowercase t is. It is not a mystery symbol, it's just how far along the spine this point is. And here's why it matters so much. Grasshopper hands us that number for free for every single rip the moment we divide the curve. Once we have it, we can feed it into a completely different formulas and get completely different results, all perfectly lined up with position along the spine. Twist, bloom, opening size, rib thickness. 4 completely different effects on the pavilion, and every one of them starts from the same number. Let's go through each one in order the way we actually built it. First step, the twist. The simple version would be rotation equals to the position multiplied by some big numbers. Flat, constant speed. The problem is that looks mechanical, like a barber pole. So instead, before we multiply t by the twist amount, we send it through the component called sine. Sine is a wave. Waves don't rise at the constant speed. They rise fast at the first, then flattened out near the top. Think of throwing a ball straight up. It leaves your hand fast and slows down the closer it gets to the highest point. So what does sine actually do here? It takes t and instead of letting the rotation grow at the one flat rate, it makes the rotation speed up at the start and ease off towards the end. That's the entire reason the twist in day 7 looks elegant instead of robotic. If we ever removed sine from this chain, the twist would still work, it just wouldn't ease. It would go back to spinning at the same flat mechanical rate the whole way through. And right after sine, there's a component called multiplication. All it does, it takes two numbers and multiplies them. Here, it takes that eased curve and scales it up by however big we want the total twist to be. Simple job, but without it, we have a nicely eased shape with actually no size to it. Quick beginner tip for remembering this. Anywhere you see a value that should feel ease or rhythmic, sine is almost always behind it. And anywhere something needs to get bigger or smaller based on the another number, that's multiplication. Now, why does the pavilion have two twisting layers, not one? A single row of identical, evenly twisting ribs looks repetitive, like a fence. So day 7 builds a second layer using the exact same ease T curve but twisting at the faster total amount. Two related motions moving past each other at different speeds. That relationship between two different speeds is what looks like a spiral staircase instead of a fence. Next, the bloom. This is the part that makes the pavilion swell wide in the middle and tapers at the ends with a little ripple running through it instead of one plain boring curve. Same starting point T, but this time it goes through sine differently to build a curve that rises from the start, peaks in the middle and comes back down by the end. Then we take T through sine a second time, but scale to wave up and down several times instead of just once. That gives us a small ripple. Multiply those two waves together, there's multiplication again. And instead of one smooth swell, we get a swell with a rhythm running through it. Much closer to how a real structural pattern looks like. But that combined signal is just a number between 0 and 1. It isn't a real radius yet. It isn't a real thickness yet. This is where remap numbers comes in. Remap numbers takes a value from one range and rescales it proportionally into a completely different range. Our bloom signal lives between 0 and 1. Remap number stretches that into whatever real radius we actually want, say half a meter as its smallest up to 4.5 meters as its widest. Without remap numbers, we'd be stuck with a value between 0 and 1, completely useless for an actual architectural radius. It's a component that turns an abstract rhythm into a real usable number. And the exact same trick, remap numbers fed by the same bloom signal, is reused to control rib thickness and again to control how wide the opening is on each rib. Same rhythm, three different outcomes. So, by this point, every rib knows exactly where it sits, how far it's twisted, how wide it should be, and how big its opening is. But right now, every rib is still completely flat, just a thin curve floating in space. Next, we give it a real depth. Because each rib is individually twisted, they don't all face the same direction anymore. So we can't just push them all the same way. Each rib needs to know its own personal outward direction. That's what Deconstruct Plane is for. Deconstruct Plane takes a rib's twisted orientation and breaks it apart into its actual direction, including the one we care about here, its own personal outward. Without this step, we would be forced to push every rib in one single shared direction, and on this twisted rib, that direction would often be completely wrong. Once we have that direction, we need to know exactly how far to push it. That's amplitude. Amplitude takes a direction and gives it an exact length. Think of it like a compass heading plus a step count. This way and exactly this far. We feed it our rib thickness value from the bloom step earlier, so ribs get pushed further where the pavilion is thick and less where it's thin. And now, finally, extrude. This is the component that actually pushes the flat rib along that direction by that distance and turns it into something solid. Think of a cookie cutter pressed into dough. A flat outline becomes a real 3D dimensional piece. Without extrude, we have a beautifully calculated shape that still looks like a wireframe sketch with no actual structure to it. So, now we have the real solid ribs, twisted, bloomed and given depth. Last step, we need a roof. Lofts take a ordered set of curves and stretches one continuous surface across all of them. Picture fabric being pulled over the row of hoops. One smooth sheet shaped by everything it passes over. Because our ribs are already in order along the spine, lofts connect them correctly on its own. Without it, we just have a set of disconnected rings, never an actual roof. And doing that exact same thing a second time on an inner layer is what gives the pavilion the second nested roof skin, visible right through the openings in the outer one. So here's the whole story, start to finish. One number, T, tells every rib how far along the spine it sits. Sine eases that number into a twist that decelerates instead of spinning flatly. Multiplication scales it. Remap numbers turns that rhythm into a real radius, thickness and opening size. Deconstruct plane finds each rib's own direction. Amplitude decides how far to push it. Extrude gives its depth. And Loft wrapped it all in a roof. 10 steps, one idea used again and again. If this made things clear, go back and rewatch day 7. I promise it will feel completely different this time. And if something's still not clear, tell me exactly where in the comments. That's generally how this video happened in the first place. See you in the phase 2.